Hello everyone, my name is Aditya Patwardhan and today I'm going to present my CSE 564 visualization final project. My SPO ID is 114394134. Now let's get started. So I'll just first give a basic rundown of the data set that I used. So since the start, I've always been interested in astronomy and astrobiology. So I was looking for data sets online related to them. And then I actually stumbled upon the NASA's Exoplanet Archives data set. This is from the NASA Exoplanet Science Institute. And I looked at it and given my interest in both these astronomy and astrobiology fields, I decided to use this data set. So I created a Python script to get a subset of this data. And that subset of the data, which I'll show you, of course, that subset of the data has nearly about 500 entries. And I also used a geo.json file, which contains all the data, but just in a JSON format in order for the world map to be seen. So this is the dataset that I have used, the NASA Exoplanet Archive dataset. And here is my code for the visuals for my final project. If you go in server, then there are three files basically. This is the CSV file, the JSON file, and my Flask backend. So this is the dataset that I got, subset of the NASA Exoplanet Archive. It contains fields like name, host name, system distance, discovery method, discovered year, basically like 2008, 2013, 1990, etc. Discovered facility, latitude, longitude, mass, radius, insolation, etc. Insolation is basically one of the methods used in astrobiology, but that's a different thing. Not a different thing, but that's pretty much I'll need to go into detail, which take up a lot of time. So anyways, we have all these metrics and features here from the NASA Exoplanet Archive. And this is the GeoJSON format over here, which also tells us how the exoplanet was discovered, where it was discovered, by what feature uh, it was discovered, etc. So I've used a React backend I've used a Flask backend with a React front end plus D3. This is my Flask backend script. Here, as you can see, there are different APIs, and then I've used all of those. And this is basically my app.js. This is used to toggle. This is used for the front end to control the front end dashboard. And if you go, API.js is just a helper file between the app.js and the other components of my components of my dashboard. So if you can, as you can see here, everything is clearly um, over here. And then the data, as you can see, is in the server folder, which is here. And then these are my different component files. So basically I have 5 different visualizations. Column selector is just selecting the columns in the banner, as you will see in the scatter plot. I'll run it. This is the PCP, which contains all of the features that I've used to display the data. This is a pie chart, which is also connected to the PCP and can select different individual, which can select the discovery method, which is also related to the PCP. And yeah, like microlensing, transit, etc. This is the world map, which I have displayed. All of these contain locations of the observatories and the observatory name, as well as satellite observatories as well, which is like Kepler and other things. But yeah, all of these contain the location of the observatories. This is a scatter plot, which is a standalone plot. And this basically contains, it is a correlation between the various features by which the observatories discovered the exoplanets, like for example, mass, insolation, distance, system distance, radii, etc. And this is also a radar chart, which is directly connected to the world map. This also displays 6 of the most prominent features, which 6 of the most prominent features, which I thought were the most important from the other features, and then gives and then displays which observatory gave more importance to which particular feature in order to discover that particular planet, or etc., or based on their details as well. So yeah, I'll show you, of course, in the visualization. But yeah, so the reason why I use the dataset, because as I said, I was extremely interested. I'm extremely like astronomy, and that's why I use this dataset. And the thing was, once I went through the data, I was just looking at the data and saw that there were two main things. The sheer pace of discovery. I mean, what I mean by that is, like, in 1990s, we just had a handful of worlds, and now if you go ahead, it's like more than it's literally in the thousands. And the second part was that the hidden patterns were also not uncovered in the column of numbers. So if you go through the data set, it's just a table format, like columns and rows. So I was thinking, what if we could go beyond those rows to get the story of each planet in, like from what the telescope that spotted it to the how its orbit is, how it rotates, or how it, what its quirks are, etc. And in order to build that, I tried to build a dashboard with Flask and D3, as I mentioned before, to try and see all of this. So yeah, okay, let me just run it first. Okay, so there are a lot of things, but since the 1992, there are various techniques which were used, like radial velocity, which is also called wobbles, or to transit depths that have unlocked a whole lot of other worlds. But most of the repos, as I said, are static, which are like tables. So my goal was to make a lens that links where we look, how we detect, and what kind of planets we find. So in order to do this, I framed my problem statement in a set of questions, which were that which observatories lead the hunt, which techniques favor small Earth-like planets, or how do feature correlation shift over time, etc. And of course, single charts or single static charts can't exactly answer that. So I built 5 linked views, which I mentioned before, explained before, and which each reveal us part of the answer of the questions previously. So as you can see here, this is basically the world map, which contains markers at each discovery facility. So for example, if we go through the facility in China, you can see it is the Yunnan Astronomical Observatory. Or if we go to Hawaii, then it is the Keck Observatory, which is pretty famous. Then there's a McDonald Observatory, which is also quite famous. And then there are Kepler. This is the infrared survey satellites. These are the satellites that I mentioned before. So this is the ESA, European Space Agency satellite. This is the Kepler. No, this is the SuperWASP. Sorry. Yeah, this is the Kepler. This is the Kepler satellite, as I mentioned before. So as you can see in the world map, there are markers at each discovery facilities. And then once we click the facilities, whatever we have clicked are showcased here. And then we can also deselect these as and when we want, however much, and basically select as much or all of them if we want to. Then this is the scatter plot, which you can see here. So this scatter plot basically has any two chosen features. For example, the default that I've kept here is the radius, which is the radii of each planet is, and then there is the orbital eccentricity. But we can basically pick and choose between each feature. As I mentioned before in the data set, as you can see, there are different features like orbit, radius, mass, orbital eccentricity, then the insolation, system distance, etc. So all of these are listed here, and we can pick and choose between each one that we want. So like, for example, orbital eccentricity is displayed over here, is the semi-major axis if we can, if we want it here. And then there would be like orbital period if we want, which is in days, of course. Then this is the orbital period, etc. Or if we want mass, then we can take the mass or whatever it is, basically. Or this is the insulation, as you can see. Then third visualization I would go over is the pie chart that I have is the pie chart. So this basically shows the discovery method by share, and it has like the discovery method basically. So transit is one method, microlensing, imaging, radial velocity, etc. And then this is linked to the PCP in a way such that this can filter the PCP to that particular method. So basically it has the, so once we click one of these discovery methods, then the PCP highlights the N planets via the current selected discovery methods batch. So if we select transit, then we can see all the planets which were discovered by transit. If we select imaging, here is imaging, so planet selected by the imaging, microlensing, etc. All of these are the things. Then, as you can see over the PCB, which I've already introduced, these have lines across the six axes, which is radius, mass, eccentricity, insolation, year, and distance. Radius, mass, eccentricity, distance, yeah, all of these six axes, along with the discovery method. And this is linked to the pie chart, as I mentioned before, and it highlights only the chosen method lines. And one more feature that the PCP has is that if we hover over any one particular line, which is, for example, if we take this one, then we can see the host or the planet ID, by which planet it was. Look at the discovery method in the pie chart, or basically the method is also highlighted in the PCP itself. So it has a hover feature as well. One more thing I forgot to mention in the world map was that I was debating putting the names of all observatories inside the map, but I realized that a lot of observatories have big names. So basically, what would happen is it will be extremely congested, overlapping, because a lot of observatories also are near to each other. So that's why I used a hover feature over here. So if you just hover over any particular point, then you can see which observatory it is. So if we go back to China, then this is the Yunnan. As you can see here is the Yunnan Astronomical Observatory, or in Australia, it is the Hat South, and the second is Parkes. These are the satellites. This is the ESA, and this is the infrared survey facility. Kepler would be here. Yeah, so you get the idea. One more visualization I have is the radar chart, which is shown by the toggle button here. What it does is basically it also has the six most important features, as I mentioned before, into it, and it gives the averages for the selected observatory. So basically what I mean by that is if I deselect every single one, then if we just use the Keck observatory, then it shows us the feature by which the planets were discovered by it. So it mainly focuses on, as you can see, stellar metallicity, radius, mass, etc. So it basically focuses more on these things rather than the other features. But if we choose a different observatory like the ESA, then it focuses more on eccentricity, metallicity, mass, but less on radius than, say, the Keck observatory. So this is how I've implemented the linking between the world map and radar chart. And of course, you can select multiple observatories at any point and look at everything. So yeah, this is how it goes. So basically, using these five visualizations, I wanted to combine to peel from the globe to a global feature relationship to method specific profiles and down to observatory level fine details. Then the implementation, as I said before, was JSON from Pandas and D3 with React as well as Flask backend. Then I would like to go into a little bit of method breakdown, which is like, as you can see here, transit, which constitutes like near to 45% um, of all the discovered methods. Then there is microlensing, which is like 15%, imaging, which is 8%, etc. And the PCP shows the transit. PCP actually, if you look closely, it shows the transit planets cluster at low eccentricity and small radius, whereas imaging basically picks up large distant giants. And then there are, if according to the map, there are leaders, which is Kepler, as I mentioned before, which is this one. Sorry, just deselect to highlight Kepler. Yeah, so Kepler, as I said, is like it spikes on small radii and short periods, but then there's the Lassilla, pardon my pronunciation, I don't know how to do it, but Lassilla or Lassia, whatever it is, which gives balanced mass and insolation. Insulation is not here, yeah, but it does give insulation, I know that. But in any case, as you can see, it shows us the feature by which it was filtered. Anyways, going back to the scatter plot, let me just distance and radius. So radius and radius versus mass, right? So mass, yeah. So as you can see here, this sandbox, sorry, the scatter plot has a it's a feature sandbox. It's a standalone plot. It doesn't link to any of the other, basically because I just wanted to give a overall view using the scatter plot by different features and then go into a little bit detail using the world map and radar chart, and then go into fine-grained analysis of the discovery method by using the pie chart and the PCB. So this is basically scatterplot is a wide-ranged view. What I mean by that is we can see each individual, what do you call it, the planets, and the feature by which it was discovered using the radius. Here is the correlation between radius and mass. So here we can actually find out that there are some supergiants in space, which we usually call super Jupiters because it's obviously quite big. So using this, we can see that this is really big super Jupiters using radii and mass, etc. So they're at moderate distances based on the other things, but we can find out such outliers. That's what I wanted to attain. And then going through the data set and all these visualizations, I also found out that there is quite a lot of detection bias, because if you can see here, transit hunts close in smaller worlds, which is evident in the pie chart and the PCP. And the radar also spikes on low eccentricity. So yeah, radar also spikes on low eccentricity, as you can see here, both for both of these things. And then if imaging while snags the exact opposite, like the giant distant planets which are visible. Yeah, imaging has a giant distant planets which are visible, like it was in the scatterplot's upper part. And then there is the method comparison where microlensing lines in PCP lie at moderate mass but extreme distances, and other methods, of course, miss those. Like all of these other methods miss those. This particular for microlensing, and there are again observatory fingerprints which basically tell you, excuse me, which basically tell you that the radar charts shows each facility's specialization, as I mentioned before. Like Keck, Keck is this one. Keck has mass precision, space telescopes, radius with period coverage. And then there are other things like the Earth, like shortlist, for example, click, transit, slice, brush PCP, etc. There are obviously a lot of real world use cases, and I would like to just mention one of them. So here is that using dashboards like these for astronomical and astrobiological purposes, mission planners uh, for example, let's just say the James Webb Space Telescope or the ESA's CHEOPS or CHOPS mission could use this dashboard to rapidly shortlist the most promising Earth-sized candidates for atmospheric follow-up. Or instead of just manually scanning tables, they can actually click the transit slice, which is here, this one, and brush for temperate insolation up in the PCP, and then select an observatory marker to see each facility's best targets on the radar chart, which basically saves weeks of preparatory work using just the um, using just tables. So I would like to actually conclude my presentation by saying that I've tried to turn a static table rows and columns into a multi-scene exploration, from the global map discovery to the feature by feature radar of each observatory. And this dashboard actually makes exoplanet science not just data, but an interactive story of our ingenuity, basically. So there are a few other future steps which I have in mind, like clustering to group the similar planetary systems, or time lapse to animate discovery over decades. But that's for later. But right now, I think I'll conclude this. Thank you for listening in. Here's my project. Please ask me if you have any questions. I'll be happy to answer them. Thank you.